Okay, so today you learn the formal definition of the derivative. The formal definition of the derivative is similar to what you've seen before. It's limit is h goes 0 of f of x plus h minus f of x all over h. How is that different than what we saw on Friday and Thursday of last week? Yeah. Instead of, we have an x instead of a. And what that means is that a was just one specific value. So every time we took the derivative, we came up with one slope value. Well, now we realize that you can take the derivative and actually come up with a function result, which is totally cool, okay? So let's just back up just one page, and let's do this, okay? So it says a particle is moving along a straight line with an equation s is equal to f of t, where s is the position and t is time in seconds. Find the velocity of the particle at those times, given the function has this position function of s equals 5t squared minus t minus 3. So, for example, when I call my wife every day as I'm headed home, she asks me where I'm at. I'm like, well, I'm at mile marker 15 on I-35. Owaton's at mile marker 41. So I'm telling her my position. I'm telling her my location. But the fact is, when you take the derivative of position, you get a rate. So if she wanted to know my derivative, she said, okay, honey, I know you're at mile marker 15, but what's your derivative? I'm like, I like the way you think. My derivative is 72 miles an hour, right? That's the way math people think, right? Yeah. She doesn't ever ask me what my derivative is, and it's one thing I feel like we need to develop in a relationship. So we're going to talk tonight about that. I agree. So, but what I love is that all of a sudden it's second semester, and some of you guys will be running around the track, and I'll say, "Hey, what's your derivative?" Some of you are like, 15 miles an hour. You know what I mean? It's like awesome. You get it. You get the idea. So no, nobody can run 28 miles an hour. Okay. So, well, one person. Okay. So anyway, so this is our position function. If you take the derivative, you get a velocity function or a rate. And I'm going to show you how to come up with that. We're going to do the limit as h goes to 0 of f of x plus h minus f of x all over h. And that will give me the derivative or the velocity function. So instead of trying to find just one specific velocity, like that 72 miles an hour, I'm going to come up with a formula that can tell you the velocity whenever you want, whether it's at mile marker 15 or mile marker 30 or mile marker 41. So what we're going to do is we're going to take the limit as h goes to 0, and we're going to plug x plus h into the function. So everywhere I see a t, I'm going to plug in x plus h. So I get 5 times x plus h, quantity squared, minus 5 times x plus h, minus 3. Oh, I'm sorry. Maybe I should look at the problem next time. All right, x plus h, and then a minus 3. Very good. So I just did the f of x plus h. Now I'm going to subtract. What do I plug in now for the function? I just plug in x. So minus 5x squared minus x minus 3. And that's all over h. Okay, this can get kind of lengthy, but that's all right. If I square this out, what am I going to get? 5x squared, 10xh, plus 5h squared, minus x minus h minus 3 minus 5x squared plus x plus 3 over h. Okay, now what? What cancels? 5x squared, negative 5x squared. Negative x, positive x. Awesome. If you remember from last year, we said if it doesn't have an h, it better cancel. If it doesn't, you did something incorrect. So now I have the limit as h goes to 0 of, can I take an h out of everything? So I get a 10x plus 5h minus 1. Are you now allowed to plug in 0? If you plug in 0, you get 10x minus 1. So in other words, our velocity function is equal to 10t minus 1. You plug the 0 in for h. The rest of the expression stays what it is. So this is really good news, because now, instead of having to do this 3 times, the question says, what is my velocity at these given times? I want to know the velocity at time, -4, I'm going to plug -4 in. -4 squared, -4 times 10 is -40, minus 1 is -41. Velocity at time 1 is going to be 10 times 1 is 10, minus 1 is 9. Velocity time 3 is going to be 29. And my measurement is in meters per second. This is a rate. So the idea is I want you to understand that because it's a velocity function, we can use it over and over again. So we're not talking about just a derivative at one point, but the derivative of an entire function. Flip it on over. So suppose I give you a graph. And I want to be able to find the derivative of that graph. Because every function will have a derivative. As you look at the previous one, look what happened. What does this shape look like if I were to graph it? A parabola. What does this shape look like if I were to graph it? A line. So in other words, if you take the derivative of a parabola, you get a line. Let's look at this example. I have a 4th degree polynomial. And here is a strategy to being able to find this type of a graph. I'm going to look at the derivative at -3, at 0, and at 2. You tell me. That's where the derivative will be equal to 0. So I'm going to choose to look at the derivative at these spots. And thank you, Claire, for asking a question, because I don't know what you're confused about if you don't ask. And unfortunately, I can't read you guys' minds. So you got to continue to ask those questions. Today is confusing for most people, but sometimes people just don't ask questions about it. So I have those points. I know that an x value of -3, that the derivative is equal to 0. Now here's what else I'm going to try to identify. Look to the left of -3. Is the derivative positive or negative? Negative. So the derivative back here is negative. How about between -3 and 0? The derivative is positive. How about between 0 and 2? The derivative is negative. And how about from 2 to infinity? The derivative is positive. So, wow. Jeez. I can't even comment. So that's what I have. The derivative is equal to 0 at those spots, so I plot those points. It says that it is negative beforehand. Graphically speaking, what does it mean to be negative? Graphically speaking, what does it mean to be negative? It means you are below the... You're below the x-axis, right? So it says, okay, the derivative is negative. This thing is negative. It sits below the x-axis. Now, I'm going to sketch it again in green so you can understand. Is the value of this function right here, positive or negative? It is negative, and as you can see, the slope of this is negative. Is the value of the function here positive or negative? As you can see, the slope is positive. Again, it's negative. Slope is negative. Value of the function is positive. Positive. Now, I started with a fourth degree. When I took the derivative, what did I get? A third degree. Before I started a second degree, I got a first degree. So every time we take the derivative, what happens to the degree? It does drop by 1. So that's something you can keep in mind. So we're going to do a bunch of examples like that. But first, what about situations where you can't take the derivative? That's where we need to identify, and then we can do all of our examples. So there are 3 classic examples where a function is not differentiable. And this function is not differentiable at a specific spot. What x value do you think this is not differentiable at? And the reason why it's not differentiable at -3 is because the derivative from the left is different than the derivative from the right. So remember we talked about limits. In order for a limit to exist, the limit from the left had to be the same as the limit from the right. Well, same case here, folks. Look at this. As you approach it from the left, negative slope. As you approach from the right, positive slope. And so anytime you have a corner, we say that that's a spot where you cannot take the derivative of it. And people might look at that, they'd say, well, the derivative is 0. You know, they like to just kind of try to balance them out. Not at all. Okay, let's look at another example where the derivative does not exist. Let's look at this example. At what x value do you think this is not differentiable? X equals 2. Why is it not differentiable at x equals 2? Very good, it's discontinuous. And if it's discontinuous, you cannot take the derivative. Finally, I'm going to do another example here. There are 2 spots where you cannot take the derivative here. What do you think are the 2 spots, the 2 x values? X equals -3 is one value at which you cannot take the derivative, and 4. Why, though? If you were to draw the tangent line, what kind of line would it make? A vertical line. And what is the slope of a vertical line? Undefined. So you cannot have an undefined value. So anytime you have what we call a vertical tangent, you cannot take the derivative. So those are the 3 classic examples. So when we get back, we'll talk about when you can take the derivative and then do what we're going to practice for our assignment today. Go get some brain food and have a good day. And in order for a function to be differentiable, that means you can take the derivative of it. There's really 2 conditions that have to be met. Number 1, the function must be continuous. Does that make sense? If it's not continuous, you can't take the derivative. And then second of all, the derivative from the left is the same from the right. So that kind of takes care of our corner situation. You can see that the derivative does not exist here, yet it's continuous. So why does the derivative not exist then? Well, it's different from the left than it is from the right. Flip it over. So we're going to do a number of things here. First of all, I'd like you to look at this first function, and I'd like you to identify where it's not differentiable. Let's start where it's not differentiable. What x values is not differentiable at? -2. Why? It's discontinuous. Where else? -1. Why? It's a corner. y0. Vertical tangent. Where else? At 2, it's discontinuous at 2 as well. Very good. You know, if it needs to a point, comes back down, you know, whether it's a, you know, kind of a softer corner or harder corner, anything like that. So we'll call that a corner. The derivative ever equal to 0 here? Yeah, f prime is equal to 0 at 1. So I'll write f prime of x is equal to 0 at x equals 1. Let's talk about where the derivative is positive. Over what intervals is it positive? Give me an example of one interval where the derivative is positive. -2 to -1. So right here, you can see that it's on its way up. Where else? 1 to 2. And the derivative is negative or less than 0. We don't know really where this goes. We'll just say from -3 to -2. -1 to 0, you can't include 0 because the derivative does not exist at 0. Then 0 to 1, and then 2 to 3. Okay, I want you to do the next one on your own. Don't worry about where it's positive or negative. For this one, please just focus on these two pieces. Number one, identify where it's discontinuous, or I'm sorry, identify where the derivative does not exist and state why. And then also identify where the derivative is equal to 0. Okay, go. Okay, so let's look at these. I'm going to say at x equals -3, we have a corner. Fair enough. We say x equals -2, it is discontinuous. I say f equals -1, it's also discontinuous, right? Now, this is one, we actually missed this during the course of second hour, and I saw it right now. That's a corner, isn't it? And it's a soft corner, but there's no doubt that that is a corner. +3, it's discontinuous as well. But what about 2? Yeah, you could call it a corner, I suppose. You could call it a vertical tangent. The fact is this is doing a barcode function piece, so technically the derivative from the left would be different than the derivative from the right. In fact, the derivative from the right would not exist. So there's a number of explanations you could give, but without a doubt, the derivative does not exist there. So you need to be careful with those type of derivatives. And the only spot where the derivative is equal to 0 is at 0. So let's try to do what you're going to be doing for your assignment today. Tomorrow you're going to be looking at those graphs again, but today I want you to focus on a worksheet. The worksheet's going to look something like this. It's going to say, sketch the graph of the derivative of each of the following functions. And so I'm going to put it right on top of this graph, okay? And when I want to sketch a graph of these functions, I need to make sure that I include where the derivative is equal to 0. I think that that's a good starting point. So I'm going to plot a 0 here. I'm going to plot a 0 here. I'm going to plot a 0 here. And sometimes it's helpful to think about what the function actually is, where it comes from. Anybody recognize that graph? It's a cosine graph, isn't it? Or a sine graph. Okay? Now, Let's look right here. Is the derivative positive or negative right here? It's positive, so the graph of the derivative will be above the x-axis. In this interval right here, is the derivative positive or negative? So it will be below the x-axis. Above, below. So I'll be above the x-axis, and I'm below. Above, below. It turns out that the derivative of cosine is negative sine, and that the derivative of sine is positive cosine. We'll show you that later on, but they are kind of related to each other. The graphs don't have to be perfect, but you know, a general idea is what works out. Okay, the second one, is the derivative ever equal to 0? The second one? No, it's not. Is there a spot where the derivative does not exist? Where? At the corner at 0. So we have to be careful of that. So derivative positive or negative right here. Not only is it negative, but it always has the same value, right? What is the slope of that line? For every, let's see, I go down 2 and over 4, right? So down 2 and over 4, so it'll be a slope of negative 1/2. Very good. And how about the slope of this guy? Positive 1/2. So my green graph is the graph of the derivative of that function. Notice I have the open circle where you can't take the derivative. Are we okay with that? How about the next one? It's a line, so it's positive, and it has a positive slope, so it'll be above the x-axis. What's the slope of that line all the time? Just give a guesstimate here. It looks like if I go over 2, looks like I go up about 1. Is that fair enough? So maybe a slope of 1/2. So slope of 1/2 all the time. So that's the graph of the derivative. So let's really get your brain thinking now. Is the derivative ever equal to 0 for this next one? Yes, where? At 0. Does the derivative ever not exist for this one? No. Okay, what can you tell me about the derivative right here at this spot? Tell me something. Anything. It's pretty small, but it's basically 0, but it is positive. So I'm going to put a dot right above the x-axis there. It's going to be positive, but just barely. How about the derivative right here? Negative, but very close to 0. So I could put it on the other side. If you were to draw the slope, it would be negative. It would go down, right? Okay. Would you say that the slope gets to be about the greatest right here? Okay, and maybe a slope of about, say, 2. So I would say slope gets to be about the greatest right there. I'll call it a slope of 2. Call it a slope of 3, somewhere about there. And then I would say the slope is the most negative right about here. I'll say negative 2. Finally, all the values to the left of 0, the graph has a slope that is positive, correct? So I will always be above the x-axis, and then the slope on the right-hand side will always be negative. So I'll always be below the x-axis. So watch as I draw this. This is an example. It's not perfect, but this is an example of what the derivative would look like. I'm always above in the first part. I'm always below in the second part. I cross over that 0. I trend off towards 0. That's what you want to be able to do come test time. To be able to take these shapes, be able to diagnose them, and draw the derivative. It's not the same process every time. I wish I could tell you what to do every single time, but I can't. Okay? But you're going to practice it, and you'll get good at it. What's the slope of this all the time? So this is the derivative. No, that will not be your test question. You try the last one on your own. This one's tricky. So here's an example of what the derivative would look like. And so gives you an idea what you want. We have one more day to mess with this tomorrow, and we're going to be using the formal definition to find derivatives. Tomorrow's very algebraic. Today was obviously very graphical, right? So that's going to be the focus of your assignment. So we're going to look at some graphs today.